What does that probe dependence tell us about the molecule and about the assay?
Okay, now I wish I had the person who wrote that, because what do they mean by silent? Do you, agonism or no effect? Let's start with agonism. There are many PAMs that, when tested in a medium to low sensitivity system, are PAMs. They shift the curve to the left. A PAM stabilizes the active state made by the agonist. However, in a very, very, very sensitive system, that could be enough to induce actual direct agonism. And so you test these in a really sensitive system, and oh my, I now have to recall it a PAM agonist because I see agonism. So the sensitivity of the system can control whether you see direct agonism or not. In terms of effect, no effect, probe dependence, this again is well known. And this one's harder to answer because allostery is a change in the conformation of a very complex being, the receptor. And there are numerous cases where an allosteric potentiates one effect to an agonist, but not a different agonist. That is the probe dependence. For example, friend of mine, Cassandra Kuhl, she tested Novo-2, which is a GLP PAM. Novo-2 has a range of natural agonists. So there's 4 of them. One is the most important one. I think it's an ester 7 to 36 or something. Another is a minor product, oxyntomodulin. She showed that Novo-2 potentiated oxynto 25-fold. Huge, beautiful. The important one, 2-fold. So there you go with probe dependence. It went the wrong way in her case because you would want the most important agonist, which is why you always have to test every agonist you think is relevant in an allosteric program, because you could get that kind of effect. Finally, allosteric PAMs and PAMs are known to frequently induce bias. So again, that same compound, Novo-2, potentiates cyclic AMP but doesn't touch calcium signaling due to GLP-1. So if you're using one signaling system, you may have the wrong one. You may see this effect with one compound, no effect with a different one. That's not really probe dependence with the external site, but probe dependence with bias. So again, you have to check as much as you can to account for it. So it's a common thing, and in terms of explaining it, that's where it gets tricky. It probably will have to do with the nuances of the changes in structure as these molecules produce various states, which, as far as I know, is not a very predictable field right now. So I'll stop there.
Thank you, Terry. I'll let you.
Do you want me to get one?
Yes.
Okay, good, cool. All right. If a molecule shows saturable binding displacement, is that sufficient evidence for an orthosteric mechanism? What else would you need to see? Interestingly phrased question. And again, I wish I had the person here. Okay. It says saturable binding displacement. When I see that, I would have assumed, no, saturable means you add a drug, you keep adding it, you keep adding it, you keep adding it, and the effect finally stops. You've saturated. I see that. It screams at me allostery. A competitive orthosteric, the more you add, the more you get. So you shift and you shift and you shift and you shift. So it wouldn't be saturable. I'm wondering if the person was asking this, though. You see a displacement curve, and it goes from where it starts to zero, which is the standard, what we call displacement. An orthosteric molecule will do that. It will, you give enough and it'll start to jump on the radioligand site when it jumps off until you displace the radioligand bound to non-radioactive. That's your standard displacement. An unfortunate thing has happened in the history of all this, because those curves have universally been called displacement curves. Okay, I see an inverse curve. But an allosteric is not doing that. It is not physically, sterically hindering. What it's doing, it is reducing the affinity of the receptors. So the radioligand that's bound, suddenly the thing it's bound to loses interest. The affinity is lower, so it washes off. It says, okay, if you don't want me, I don't want you. And so it's not a physical steric hindrance, it's a change in the sensitivity of the protein, but it gives you the same thing. The inverse S-shaped so-called displacement curve. So I'm wondering if our person was asking about that. You see a displacement curve that is in no way evidence you've got orthosteric displacement. Just like shield, you can get the same thing with a NAM, and you have to do separate experiments to work that out. So I'll stop there.
I'll let you pick another one. Someone in the audience have questions.
Okay. Oh, how does knowing the binding mode change the way you design your in vivo experiment studies? Well, okay, so I keep harping about it's very important to know if your molecule is orthosteric or it's allosteric. And those of you who have heard me talk on this will roll your eyes and say, oh, it's the same thing, but it's true. An orthosteric will hijack the target. It will eliminate the natural signaling and preempt it with your molecule. So the molecule will impose its own efficacy on the system. An allosteric may not do that. It may, but it's going to be in partnership. So you're going to get more complex array of physiology, possibly, with an allosteric. So that's the first thing. Secondly, I always argue it could be important to know an allosteric because you may encounter saturation of effect. And this can be a good thing, bad thing. Bad thing if you don't get enough effect. Oh gosh, I poured in the compound and all I see is a twofold shift. That's it. Many systems, that's it, enough. Valium produces a 2.5-fold potentiation, and that's enough. Yet it's not too much. The calcium sensing receptor PAM effects. Cells hate calcium. If you potentiate calcium too much, you will get a terrible toxic effect. The strength of an allosteric is you can choose one that has a small alpha beta index. So, for example, there are potentiators of calcium producing a 10, 12, 15-fold effect, and they're toxic. There's one that produces a 2.5-fold shift. You can't get an overdose of this stuff. It just gives enough. And that happens to be the approved drug, cinacalcet. So you can, knowing you have an allosteric, unlike an orthosteric, which the more you give, the more you get, you can overdose here. You might choose the right compound to not get an overdose. Moreover, knowing that, you can fill up the system. You can give a huge dose to increase duration without producing an overdose. So that's really important to know if you've got an allosteric effect or not.